Okay, so what we're going to be doing today is going over acid-base neutralization. So the objective of the video, there's two. The first is to review the concept, and the second is to do examples. So hopefully by having a visual of our acid-base neutralization reactions, we can get a better understanding of what we have to do. So in all acid-base neutralization reactions, our products are always going to be the same. We're always going to create water, and we will always create a salt. Now, a recap, a salt is an electrolyte that's formed of a metal and a nonmetal. So examples of salts are classic sodium chloride or table salt, and we have examples like magnesium bromide and calcium fluoride, just to name a few. But there's a huge variety of salts. Water, we remember, is just our classic H2O. Now an acid is starts with a hydrogen ion and ends with a nonmetal. So examples: hydrochloric acid, nitric acid, and sulfuric acid. Those are examples of acids. And bases start with a metal and they end with a hydroxyl ion. So our example, sodium hydroxide, which is our key base, and here we go, potassium hydroxide. So whenever you mix an acid and a base, you're always going to produce salt and water. So how do you produce salt and water? Well, we'll see it in the next slide. So our first example is going to be an acid-base reaction between hydrochloric acid and sodium hydroxide. Now, the key to all of these reactions is that when acids and bases are dissolved in water, they dissociate into their ions. So what does that mean, dissociate into ionic form? Well, it's quite simple. When hydrochloric acid is dissolved in water, it splits up into H plus and Cl minus. The same thing with sodium hydroxide. When it's dissolved in water, it also splits up into Na plus and OH minus. Now, just a reminder, why does Na have a positive charge? Well, it's because Na is in group 1. So that means to get a full valence electron, it has two choices. It loses its last valence electron, or it gains 7. Now, atoms are lazy. They're going to do the least possible amount of work to get that full shell, and in sodium's case, it's going to lose that valence electron, so it has an overall positive charge. Because if it loses its valence electron, remember, it'll have 11 protons, 10 electrons, and our protons have a positive charge, our electrons have a negative charge, so it has an overall charge of +1. Same thing with chlorine. Why does chlorine have a negative charge? Well, chlorine is in group 7, so that means it has 7 valence electrons. Same concept. Is it going to lose 7 valence electrons or gain 1 valence electron to get a total of 8? Well, in chlorine's case, it's going to gain 1 electron, so it will have an overall negative charge because chlorine has an atomic number of 17, so that means 17 protons. If it's gaining 1, it's 18 electrons, 17 protons, 18 electrons, gives us an over of -1 charge. So you might be wondering, why do the charges matter? Well, the thing is, in a molecule, you have to have an overall charge of 0. So that means all of your positives and all of your negatives need to add up to 0. So if we notice in our original molecule of hydrochloric acid, if we look at the charge, hydrogen has a +1 charge, chlorine has a -1 charge, +1 minus -1 gives us 0. So that was an overall net charge of 0. Same thing over here. Sodium has +1 charge. The hydroxyl ion has a -1 charge, so 1 minus 1 gives us 0. So this is when we had our base and our acid before reacting. So the same thing must apply, that in our final products, we also have to have our overall charge of 0. Now, when we have an acid and a base reacting, what's actually happening here is called a double displacement reaction, which is just a really fancy word for saying that the elements in the initial molecules just switch partners. And the partners that they switch it with have to be very, very specific. So if we notice, hydrogen has a positive charge and it's connected to chlorine, which has a negative charge. So if it's switching partners, the hydrogen still needs to be bonded to something with a negative charge, but not with chlorine. It's going to switching partners. Now, out of our 4 ions, the only one that has a negative charge left over is our hydroxyl ion. So our hydrogen is going to be now attracted to our hydroxyl ion. Same thing over here. Our sodium has a positive charge, and it's going to have to bond to something with a negative charge. Now, the only other ion that's available that has a negative charge is chlorine. So sodium is going to be bounded to chlorine. So let's look at this whole bonding of our different ions on the next slide. Okay, so we see here our partial equation of our acid and our base, and right below we have just basically ball and stick models of our acids. So we have our hydrogen ion, our chlorine ion that makes hydrochloric acid, and we have our sodium ion and our hydroxyl ion that makes sodium hydroxide. So basically, as I said, it's just basically our switching of pairs. So our hydrogen ion needs to be connected to something that has a negative charge. So it's not going to go to chlorine, but it is going to go to our hydroxyl ion. Same thing. Our chlorine needs to be bounded with something that has a positive charge. Now, it's not going to be the hydrogen because it was already bounded to the hydrogen. It's looking for a new partner. So this new partner is going to be with the sodium. So these two products that we have right here are our new molecules. So this one down here, 2 H's and an O, is H2O, which is water. And this molecule over here, on top, Na and Cl, form NaCl, which is our salt. So our hydrochloric acid plus sodium hydroxide form NaCl plus H2O. Now, another thing that's important is if we look at it, the overall charge of our molecule is 0. The Na has a +1 charge, the Cl has a -1 charge, so 1 minus 1 gives us 0. And also down here, the hydrogen ion has a +1 charge, the OH has a -1 charge, so our overall charge is 0. So we know we've done it right. So now what we're going to do is we're actually going to look at another example. Okay, so basically we're going to do another example. So as we see right here, we have this molecule right here, which is, yeah, you guessed it, an acid. And it's going to be reacting with this molecule right here, which is, yep, that's also a base. Now, you're probably wondering why this is a base, because it's not following the normal rule where you have a metal plus a hydroxide ion. The reason why is because this is your only exception. So what we're going to do is we're actually going to look at hydrochloric acid and ammonium hydroxide when it's dissociated from its ions. So we're going to look at it in its ion form. Okay, so we have hydrochloric acid split up into our hydrogen ion and our chlorine ion, and we have ammonium hydroxide split up into our hydroxide ion and our ammonia ion. Now, you might be wondering, how do I know that this has a positive 1 charge? Now, important to remember, our hydrogen ion has a +1 charge because even though it is not in the alkali metals, so even though it's not in group 1, it has the same tendency as everything in group 1, and that means it will lose its valence electron to have an overall of +1 charge. Our hydroxyl ion has a negative charge. So from this piece of information, we can deduce what any of the polyatomic ions that are connected to either our acids, so anything that has a hydrogen ion, or to our bases, anything that has a hydroxyl ion. Now, the thing is, remember, just like I said before, all of our molecules have to have a net charge of 0. So if our hydroxyl ion has a negative charge, and we only have one ammonium ion, then by default, the only way that we can have a -1 end up to 0 is if we have a +1. So that's why our charge is +1. So we have our changing of our partners. Our hydrogen needs to go with something that has a negative charge. It's not going with chlorine, so it's going to our hydroxyl ion. And our chlorine needs to go with something with a positive charge. Well, it's not moving with hydrogen, so it's going to go to the next best thing, so the other thing that has a positive charge, which is our ammonia ion. So what we make is the following. We make ammonia chloride, so this molecule right here, which is a salt, and our trusty H2O, which is our water. Now, the examples that we've seen here has always been a 1-to-1. So what I mean 1-to-1 is that all of our ions have either a +1 charge or a -1 charge. The next example that we're going to see is we're going to see something where one of our ions has a +2 charge. And let's see how that changes some things. So here we're going to look at the reaction between hydrochloric acid, HCl, our trusty hydrochloric acid, and the base in this case is barium hydroxide. Now, this is where I said that we're going to be using something that doesn't have either +1 or a -1 charge. Well, hydrochloric acid, we already know that our hydrogen has a +1 charge, and our chlorine has a -1 charge, partly because of hydrogen has a +1 charge. Then by default, our chlorine has to have a -1 charge because they need to cancel out. Or, if we remember, chlorine is in group 7, so its tendency is to gain 1 electron, so we'll have an overall charge of -1. Now, let's look over here. We have barium hydroxide with a 2 over here. So we have 2 clues here. First clue is barium. Now, if we look on the periodic table, we'll find out that barium is in group 2. Now, everything in group 2 means that they have 2 valence electrons. So if we remember with our octet rule, all of your atoms want to get a full last shell. So barium has two options. Option number one is gain 6 electrons, or option number two is lose 2 electrons. Now, again, atoms are lazy. They're going to choose the option that requires the least amount of work, so it chooses option number 2, lose 2 electrons. So if I'm losing 2 electrons, that means I will have 2 more protons than electrons. So if we look on the periodic table, barium has 56 protons. If I'm losing 2 electrons, that means I have 54 electrons. My overall charge will be plus 2. So we know that barium is going to form an ion of barium plus 2. So that's clue number 1. Now, clue number 2 is, let's count our hydroxyl groups. We actually have 2 OH minuses. Now remember, OH minus, each one has a -1 charge. So if I have 2 OH minuses, that means my overall negative charges is 2. What number do I add to -2 to get 0? And yep, that's right, it's going to be positive 2. So the only way that I can cancel out my 2 negative charges is if my metal has a positive 2 charge, which in actuality it does. Okay, so just again, we're doing our swapping of our partners. So we have our hydrogen with a positive charge. It needs to be bound to something that has a negative charge, because again, opposite charges attract. So our hydrogen ion is going to bond with a hydroxyl group. So now, same thing, our chlorine ion has to bond with something that has a positive charge. So the only thing that's left is our barium. So these two are going to bond. Now, we have a problem. There's 2 things that have a charge imbalance. Our first thing is our hydroxyl ion. It still has a -1 charge. Now, to be a molecule, it has to have an overall charge of 0. So that means I need to have another positive charge come in. And our second problem is right over here. Our barium chloride, well, we still have a charge imbalance because barium is in group 2. So that means it loses 2 electrons. Chlorine is in group 7. That means it gains 1 electron. So right now we have an overall charge of +1. So we need a solution. So we need to have another chlorine come in here. We need to have another chlorine come here to get rid of our charge imbalance. And we need to have another hydrogen come here to fix our charge imbalance. So what that means is we need to have another hydrogen chloride. So another hydrogen ion, a hydrogen chloride molecule comes in, and it's going to split up into its ions, just like it did before. So I'm going to have H plus and Cl minus being formed. So again, dissociates. We're going to remove this so it's not confusing anymore. And now this hydrogen ion is going to go with this hydroxyl group, which will now fix our charge imbalance. And it has a net charge of 0, so that's good. And our chlorine ion is going to come over here and fix this charge imbalance. So now that we have a net balance of 0, so we're good. So if we evaluate in our final products, we get barium chloride, which is 1 barium and 2 chlorine atoms, and we get 2 water molecules. So the balanced chemical equation looks something like this. So we have 2 HCl's plus 1 barium hydroxide gives us 1 barium chloride plus 2 water molecules. Now the reason why we have 2 hydrochloric acids is because, remember, we needed to have an extra chlorine to go with the barium, and we needed to have an extra hydrogen to occupy the hydroxyl group. I hope this clarifies some questions that you might have on acid-base neutralizations. In the next video, what we're going to be doing is we're going to be doing more practice problems, but the practice problems that we're going to be doing is with ions that have either +2 or +3 charge. Okay, thank you.